Okay, so what we're going to try to do today in this video is pull together what we've seen about polynomials and put that with the graph of a polynomial. Okay, so um, we'll be going through a good bit of the notes in section 2.3 so you can follow along. And we'll start with just a reminder of really some things that we've already talked about. It says each monomial in a sum is called a term. So when we talk about a monomial, we're talking about a combination or a product of a constant and a variable raised to some power. Okay, so 5x squared is a monomial. 10x cubed is a monomial. It's one term, right? There's no plus or minus in there. All right, so each monomial in a sum is called a term. All right, notice it says sum there. So sum is basically separated by a plus sign, or we could say a minus sign if we're doing plus or negative. But anyway, we're talking about those little pieces that are terms. Terms of a polynomial written in descending degree is said to be in standard form. Okay, also a coefficient is the constant or the number value of each term, that number that's out front, that's not the exponent. So when we say 8x to the fourth, 8 is the coefficient. Okay, the highest degreed monomial in a polynomial is called the leading term, and the constant is a number without a variable. All right, so this is pretty much information that we already knew, but good to know. Okay, so we talk about the leading coefficient, and it says power functions eventually rise or fall without bound as x moves toward infinity, left or right, so to plus or minus infinity. So what they're saying is that when we're talking about x to the 7th, x to the 9th, x to the 100th, in the middle, it can go up and down like a roller coaster, but eventually that function is going to either keep going up or keep going down, as it goes towards, x goes towards infinity or minus infinity. All right, so how do we know? This is what we call end behavior. How do we know how the function behaves on the end of its graph? And there are two things that we're going to look at to determine that. First of all, the degree of the function will let us know how it behaves on the ends. And we're going to be looking at whether or not the degree is even or odd. And then we're going to be looking at that leading coefficient. That's also going to have an impact on which way the function goes. All right, so let's take a look at just kind of a summary. And in this summary, the first picture here, notice that we're talking about a situation where the leading coefficient is positive and n, which is going to be the degree of the polynomial, is odd. Okay, so we got a leading coefficient that is positive and our power is odd. All right, so what they're telling us is that the function looks kind of like this. Think about the x cubed function. If you remember what that function looks like, okay, it was up on the right and down on the left. All right, and that was just basic x cubed. If we add in there an x squared and an x and a constant, then we get a little extra of this up and down in the middle. But this describes the end behavior. All right, so any function that has an odd power, we're talking about polynomials. So when we have a polynomial that has an odd power as its degree, then the end behavior is going to look like this when the leading coefficient is positive. So as x approaches infinity, f of x goes to infinity, right? As we're getting x larger and larger, so is y. And as x approaches minus infinity, f of x is going to go to minus infinity. All right, so that's what happens when the leading coefficient is positive and the power is odd. All right, if we make that leading coefficient negative and the power is still odd, it just flips the whole thing over the x-axis, right? So now we can say as x approaches infinity, f of x goes to minus infinity. And as x approaches minus infinity, f of x goes to positive infinity. Okay, so we've talked about the case when the power or the degree is odd. All right, so now let's look at what happens when our degree is even. Okay, so in this case, we've got a positive leading coefficient and an even degree for our polynomial. And in that case, I think about x squared, right? X squared is a polynomial where we have a positive coefficient and an even degree, and we know that just looks like a parabola that opens upward, right? So that is up on the left and up on the right. And so for any polynomial that has an even degree, the end behavior is going to act in that same way. So we can say as x approaches negative infinity, f of x goes to positive infinity, and as x approaches positive infinity, f of x still goes to, it's up on both ends. Okay, if that leading coefficient is negative and the power is even, then it's down on both ends. All right, and so we can tell about the end behavior based on the degree of the polynomial, whether it's even or odd, and then also we're going to look at the leading coefficient to see if it acts like that basic function of x cubed or x squared, or if it's going to be flipped over the x-axis. All right, so just to kind of summarize, it says consider the domain and range for each degree family. And by degree family, we're talking about whether it's an even degree or odd degree. Okay, and so it says as x approaches infinity and x approaches negative infinity, what do you notice about f of x or the y value of the graphs? And it says on even powers, the end behavior is the same, right? And then on odd powers, the end behavior is going to be opposite. So this question says, how does the value of the leading coefficient a affect the value as x approaches infinity and x approaches negative infinity? And we said if a is less than 0, then the end behavior directions change. Okay, and that's what we saw in the illustration on the previous slide. All right, and we'll come back to that when we put it with some other things that we're learning. All of these little things, they're small, but when we put them all together, they help us to figure out what this polynomial looks like. So you want to almost think of this as a puzzle or a mystery, and we're paying attention to little things like the degree of the polynomial or the sign of the leading coefficient, or as you can see, we're going to talk about multiplicity in just a second. These things tell us a lot about what this polynomial is going to look like. So here's another little clue. It says the graph of f has at most n minus 1 turning points. Turning points are places where the points on the graph changes from increasing to decreasing or vice versa. So if I know the degree of my polynomial is n, then at most I can have n minus 1 turning points. Okay, and the second thing is the function f has at most n real zeros. Okay, so when I look at the degree of the polynomial, it tells me how many zeros, real zeros, I could potentially have. That's what we've been kind of working on up to this point, is finding the zeros of the polynomial. Okay, we've done a pretty good job of finding real zeros, but remember that they don't have to all be real zeros. And that's why it says at most n real zeros. Okay, if it's not a real zero, it could be an imaginary zero. And we'll talk more about those a little bit later. Okay, even in odd multiplicity, if a polynomial function has a factor that is repeated, these duplicate roots are labeled as a multiplicity of n, or whatever the power is. So if I've got x plus 5 to the third power, then x plus 5 has a multiplicity of 3. right? And so that lets me know something about how the graph is going to behave at x minus 5. All right, so how is that? If f has a 0, c of odd multiplicity, then the graph of f will cross the x-axis at c0. All right, so if we've got repeated factors and it's repeated an odd number of times, then we're actually going to cross the graph. Whereas if the multiplicity is even, it's going to touch the graph at that 0, but it's not going to cross it. And we'll see several examples of this to kind of clear this up. All right, so let's look at these two polynomials, and then we'll look at what the calculator shows us to kind of verify what we think. All right, so in A, we've got f of x equals negative x cubed plus 2x squared plus x plus 1, okay? So we're going to analyze this. First of all, n in this case is 3. It's odd, right? So that already gives me some idea about what this function should look like. But then I also noticed that a sub n, or my leading coefficient, is negative 1, right? So that means it's going to be up on the left and down on the right if we think about the basic x cubed pattern. How do we write that in calculus and pre-calculus? What we can say is as x goes towards negative infinity, which is on the left, then f of x is going to go to positive infinity. And as x goes towards positive infinity, which is on the right, f of x is going to go to negative infinity, okay? At most, we would have 3 minus 1 turning points. Okay, remember we said at most we have n minus 1 turning points. Okay, so we got 2 turning points at most. All right, so let's see what it looks like. Here is the actual graph of the function. Okay, remember we said on the left it would be up and on the right it would be down. Okay, and here we can see we've got those 2 turning points. Here's one where it went from decreasing to increasing, and then we're going to decreasing again. So here's the second one. 1 turning point, here's the second turning point. All right, and so we knew a lot about what this graph should look like even before we used our calculator to find it. All right, in this one, we've got x to the 4th minus 3x cubed plus 2x. So in this case, n is even, all right, and a sub n is positive, right? That's a positive 1, all right? So with even, we know it's going to be the same on the left and the right. Because the leading coefficient is positive, then I know it's going to be up on both the left and the right. So we can say as x approaches negative infinity, f of x goes to positive infinity. And as x approaches positive infinity, f of x approaches positive infinity. It does the same thing. All right, and then with this one, we would have at most 3 turning points. Okay, so if we look at our graph, looks something like this. We can see that it's up on both the left and the right, and we've got 1, 2, 3 turning points. All right, so let's talk a little bit more about that multiplicity, okay? When we look at this particular function, it's already factored for us, but we can see that x plus 2 has a multiplicity of 3, okay? Because that is odd, that means, well, we're going to be looking at all of these things. We're going to look at the factor. So we've got x plus 2. That corresponds to a 0 of x equals negative 2. And the multiplicity is odd, right? And so based on what we were told, what we can expect is that we will cross the x-axis at negative 2, 0. Okay, we're going to actually cross it. All right, versus here we had a factor of x minus 1, which corresponds to a 0 of x equals 1. Well, we see that it has a multiplicity of 2. right, which is even. And so it's going to touch the x-axis, but not cross at 1, 0. Okay, and so you have, I believe, this graph in your notes already. Here we are at -2, and we can see that we are crossing the x-axis, right? And that's because for x equals -2, we had a multiplicity of 3, which is odd. But at x equals 1, we just touch it, right? It comes down, it hits it, and it goes back up. It does not go across. All right, so x equals 1, we have a multiplicity of 2, and you can see we touch it, but we don't cross. So do you see how just looking at the polynomial, we can know so much about what the graph is going to look like? Okay, let's talk a little bit about maxes and mins. It says at a local max, the graph changes from increasing to decreasing. Okay, on the graph at the right, they want us to shade the intervals of increase in green. So it was increasing here, right? Because as we go from left to right, I can see that the graph is going up. And then it also increases from here to here. Okay, so I've shaded that part in green. Okay, and we've got decreasing from here to here. Okay. And you can kind of already tell I'm going to have a max, a relative maximum value here, a relative minimum value here. But let's take a closer look at those definitions before we get too much into that. Okay, so it says for any function f, if there exists an interval x1 to x2 that contains c, so that for all x not equal to c in the interval, then f has a local max at c when f of c is greater than f of x. And f of c is called a relative or a local maximum of f. Okay? So basically what it means is that for a certain interval, we get to a maximum point. And in if it's a minimum value for the interval, we call it a relative minimum, okay? Before we look at it on the graph, I want to point out that the max and min are f of c's, right, or basically our y values. We can talk about where it occurs, which would be an x value, but the actual maximum or minimum value is a y value. So on this graph, we've got the relative max really occurs at two different x values. It occurs at about x equals -2 and x equals +2, but the actual maximum value is 5, right? Okay, and that's a relative max. These didn't have to be the same. We could have a relative max over here and another one over here. All right, and then the relative min occurs at x equals 0, and it is 0. All right, so for a certain interval, this is the minimum value. Okay, it's not the overall minimum, it's just the minimum for that interval. Okay, so one of the first things you're going to see in Delta Math is kind of looking at, everything about the degree, the leading coefficient, the zeros, and the relative minimums and maximums. Okay, so for this particular graph, we're going to fill in this form. They ask us about the degree of f of x, and because it's behaving the same on both sides, I would say that the degree is even. Okay, the leading coefficient, since it's up on both sides, the leading coefficient is positive. Okay, and I have 1, 2, 3 real zeros. Okay, my zeros are where I'm crossing or touching that x-axis. So that's at 1, 2, 3 places. Okay, and I have 2 relative minimum values. There's a relative min here and another relative min here. Okay, here's another example. Looking at this one, because it behaves differently on the left and the right, I can say that the degree is odd. Right? I can see that this is flipped over from my basic behavior of x cubed. So I'm going to say that the leading coefficient is negative. Okay, the basic x cubed graph, and you can look back at your parent functions, but it looks kind of like the way I just traced my cursors, up on the right and then down on the left. Okay, this is the opposite of that. So that's how I know it has a leading coefficient that is negative. Okay, and I'm either touching or crossing the x-axis at 1, 2, 3, 4 places. So I've got 4 real zeros, and it looks like I have 1, 2 relative minimum values. All right, so moving on to another activity, what we want to be able to do is try to match the graph to an appropriate equation. And of course, we're going to go from the equation to the graph. But in this one, first of all, I could say that this is going to have an even degree, right? Because it's behaving the same on both the left and the right. All right, so I could eliminate this choice because this would have a third degree. All right, and then I noticed that I only have one zero, it's -3, but I am touching, not crossing, so the multiplicity of this has to be even, right? And so when I look, a 0 of -3 corresponds to a factor of x plus 3 with a multiplicity that is even. And so the only one that fits that here would be this choice, all right? Because again, it touched at -3 but did not cross. I knew that my multiplicity had to be even, all right? And this is the only one that gives me a 0 of -3 with an even multiplicity. All right, let's look at another. Which equation could represent the graph shown below? All right, so looking at this, I would be concerned about the different zeros that I have. I've got a 0 at 0, I've got one at 2, and I have another at 6. All right, so I need a polynomial that has factors that would lead to these 3 zeros. Okay, and so I could get x equals 0 from just x. I could get x equals 2 from this and x equals 6 from this. So this would be the correct answer. And we know that it has to have an odd multiplicity because it is, actually this is wrong. It actually does cross, right? It's crossing the x-axis. So the multiplicity is odd, and that matches this particular answer. All right. Okay, so yes, make sure you note that it crosses at 0, 2, and 6. They each have, that means they each have an odd multiplicity, and so that matches this answer. Okay, so in this equation or graph, I'm going to identify my zeros. Looks like I have a 0 at -8. Notice at -8, we're touching but not crossing. So that lets me know to expect an even multiplicity for, this would be x plus 8 as a factor. All right, and then over here, we're going to actually cross at 5. So when I look through, the only place where I see that I have an even multiplicity for x plus 8 is here. And so this would be my choice. And notice that we've got an odd multiplicity for 5, which matches with the graph because we actually cross there. Okay, and this one we are looking at our zeros, and this one's a little bit different. because these first two zeros, we don't even know exactly what they are, right? They fall kind of between 1 and 2 and -1 and -2. But we do see that the graph crosses at x equals 8, which means we're going to have an odd multiplicity for x equals 8, or the factor would be x minus 8. All right, so I could narrow it down to these first two choices based on the x minus 8 crossing at x equals 8. All right, but then what about, how do I decide between these two choices? Well, the thing is that these two solutions, they may not be nice numbers, but they are real solutions. They're real numbers, right? And so I might want to look to see which of these two choices is going to give me real solutions versus imaginary solutions. And it would be this one, right? If we solve this, we would get x squared equals the square root of 2, and that's going to give me two real solutions. Versus if I solve this one, we get x squared equals -2. And so that's going to lead me to two imaginary solutions. And that's not what we have in this case. So this would be our correct answer. All right, we're almost done. Here we have another graph. I'm identifying the zeros, and we're crossing at each of these zeros. So each of them should have an odd multiplicity. Okay, we're crossing at -8, -2, and +8. All right, so kind of looking down here at my choices, just based on the -2, again, it's got to be one of these first two. All right, but where does that -8 and +8 come from? Well, this is not a linear factor, but if I solve this using, let's say, our method for square roots that we talked about, we get x squared minus 64 equals 0, x squared equals 64, or x equals plus or minus 8. And those are the zeros that we have, and they each have a multiplicity of 1, right? There's 1 for x plus 8, 1 for x minus 8, and so this would be our best choice. All right, here's another one. Looks like we're crossing at -1, and we're touching at 5. All right, so if we cross at -1, we should expect an odd multiplicity. All right, so I can eliminate these because they're both even for 1 or -1, right? So it's going to have to be one of these. At 5, I'm touching, all right, and that's at +5, so the factor is x minus 5, right? And so this would be the best choice because we're going to have an even multiplicity here, which means I touch at 5, but an odd multiplicity here, so I'm going to cross at -1. So this is the correct choice. All right, and that's it. So check in Schoology to see what the assignment is, work on it, try to get it done to the best of your ability. But if you have any questions about it, you can ask about them during tutoring. If you'll just email me and let me know that you want to meet during the tutoring time, we can do that, or you'll have an opportunity to ask questions about this on Tuesday as well. This assignment will be due on Tuesday at the end of your class. So yes, please go ahead and try to get as much done as you can. But if you have questions, you can get help during tutoring, or we can talk about it a little bit on Tuesday when we have our next class.